All right. Hello, everybody. So together with Leslie and Daniel and Jo van Bulck, we published this paper on WeMu. And WeMu is a tool that we built for emulating microarchitectural weird machines. Now, I already hear you thinking, Dries, microarchitectural weird machines, what is that? I've never heard of it. Let me explain. So what we see here on this slide is a fleet of ships. They are military ships and they're on a mission, right? And as we know from the movies, in every one of these ships, there's like a large control room full of people continuously analyzing the alerts and scanning the surroundings. So these people know very well what's happening around them, at least what's happening around them above the surface level, because monitoring what's happening below the surface level is a lot more difficult. And I think that's a great representation of our ISA stack. Above the surface level, we have the architectural layer, where everything is documented and it's relatively easy to see and know what's going on there. But below that is a microarchitectural layer in which the rules are a lot more vague and it's much harder to see what's happening there because a lot of details are abstracted away by the architectural interface. And so let's put our malware analyst hats on and let's look at this from a malware analysis perspective. And then you could say that these control rooms are actually malware analysis tools like emulators, symbolic execution analysis tools, and debuggers. And you might feel it coming already, but there is something that these tools don't know. And that is below them, there is a large and scary submarine. A submarine also known as a microarchitectural weird machine. So a microarchitectural weird machine uses only microarchitectural components to exist and to operate. And therefore, our tools above, which traditionally only monitor the architectural layer, cannot be used to analyze or observe the submarine. Now, recently, we have seen, of course, extensions of these tools, including microarchitectural monitoring, but it remains too inaccurate or too incomplete to properly analyze microarchitectural weird machines. Now, what is it exactly that makes the submarine so scary? Why are microarchitectural weird machines dangerous? Well, microarchitectural weird machines are essentially Turing machines performing hidden computations using microarchitectural side effects. That's a mouthful, but because they're Turing machines, we can reason about them using two components, storage and compute. Now, these Turing machines are implemented using microarchitectural side effects. Specifically, they use the cache state for storage, and they use transient execution and out-of-order execution for compute. Now, one very important keyword in this definition is hidden. So these Turing machines perform hidden computations, meaning that they can be used, for example, to obfuscate malware. And this is something that previous papers have shown already. Now, one thing you would typically do to analyze obfuscated malware and hidden computations is throwing it in an emulator, because an emulator gives you visibility into the computations. But there is a problem with that, and Evtushkin et al. Have stated it in a previous paper. They have stated that emulating the effects that microarchitectural weird machines use with an acceptable precision is extremely difficult, as it would require first to reverse engineer the target hardware platform. And the statement made us think, well, do we really need to reverse engineer the target hardware platform? Do we really need an accurate representation of the microarchitecture? And what if instead we use abstract models? Abstract models of the microarchitecture which focus specifically on those microarchitectural side effects that those weird machines use. And that is what brings us straight to our paper contribution. We are introducing WeMu, and WeMu is the first framework for analyzing microarchitectural weird machines using emulation. Specifically, WeMu gives us insight into this black box of microarchitectural weird machines by emulating the cache state, transient execution, and out-of-order execution using abstract models. Now, for the implementation of WeMu, we chose to extend Unicorn. And Unicorn is an ISA-level CPU emulator that probably many of you know. A Unicorn is very lightweight and extensible, and importantly, it doesn't have a microarchitecture, allowing us to plug in our own abstract models of the microarchitectural components. Now you might ask, okay, then why don't you use a full system emulator? It's a fair question because full system emulators have the goal of emulating the microarchitecture with as much accuracy as possible. And we demonstrated in our paper that Gem5, a very prominent full system emulator, is extremely slow, very complex to work with, and most importantly, it does not emulate microarchitectural weird machines correctly out of the box. So let's dive a little bit deeper into the implementation of WeMu and how it emulates microarchitectural weird machines. And let's look at storage first. So microarchitectural weird machines need to encode their data into the cache state, and they do that specifically using weird registers. And in a weird register, the state of the register is linked to the cache presence of the variable. If the register is in state 0, the variable is not in cache, and in state 1, the variable is in cache. And you can change the state of the register by loading and flushing the variable, and you can read it by performing a timed memory read. If your read is slow, the variable was not in cache, so it indicates a 0. If your read was fast, the variable was in cache, and it indicates a 1. Now, in order to emulate this, we need to extend Unicorn with a model of the cache. And one thing we could do is implement a cache model that resembles a real hardware cache with as much accuracy as possible. But that would be pretty difficult because real hardware caches consist out of multiple levels in which every level is organized in a set associative way. So instead what we can do is we can try to find an abstract model by looking at the specific microarchitectural effect that is used by weird registers. And this effect is only the cache presence of variables. So it doesn't mean in which level or set this variable is. And because of that, we are able to just emulate the cache using a single level infinite cache. And this significantly reduces the implementation complexity as well as the emulation overhead, while still being able to accurately or correctly emulate weird registers. Now let's move on to the compute layer. And in the compute layer, these weird machines use the weird registers and compute on them using so-called weird gates. So those are simple logical gates, which are implemented using transient execution and out-of-order execution. So explained very simply, transient execution exists because modern CPUs are continuously trying to execute instructions from the future in order to keep themselves busy and increase the performance. Now, in some cases, those instructions executed from the future end up not being necessary. And in those cases, CPUs need to roll back the effects, but this rollback only applies to the architectural effects, and the microarchitectural effects persist after the rollback. So what these weird machines do is they deliberately trigger transient execution, and they use it to perform computations which remain architecturally invisible and leave their results behind in the microarchitecture. And these transient triggers that they use for that, they are not new, and we already know them from previous attacks like Meltdown, Spectre, Foreshadow, and Zombie Load. Now let's look at our first gate, which is a weird AND gate. And you can see that in the first line there is a division by 0, which will cause an exception, but before that exception, before the execution is transferred to the exception, the second line is already executed transiently. And what we try to do in this second line is we try to write a variable to the we try to write a value to the output variable, but we first need to load the two input variables. Now keep in mind that these are weird registers, so it's only their cache presence that we're interested in, not their architectural value. So let's look at the first case where both inputs are 1, which means both inputs are cached. In this case, we can load them fast enough to cache the output variable before the rollback happens. If we compare that to the second example, where one input is not cached, well, then loading that input takes too long and it exceeds our transient window, and the rollback will prevent us from caching the output variable. This is exactly the AND gate behavior that we're implementing. Only if both inputs are cached, the output will also be cached. Now, in order to emulate this in WeMu, we need to extend it with 3 things. We need to emulate the transient triggers and the rollbacks, for which I will refer to the paper, and we need to emulate those data races. Now, for the data races, we need to be able to emulate correctly the length of the transient window and the length of the memory operations. And we will use configurable parameters for that. And again, there is an insight that we can use by looking at the microarchitectural effect, and that tells us that only the relative timing matters, not the absolute accuracy. So what does that mean? Well, we don't need cycle-accurate modeling for the transient window length and the memory operations. Instead, we just use parameters that we configure itself, and we need to make sure that those are correct relative to each other. So this is what we came up with. Normal instructions and cache hits are length 1, which are significantly shorter than a transient window of length 250, and a cache miss is longer than a transient window. So as soon as a cache miss occurs, the transient window is exceeded and the other instructions cannot execute anymore. And again, this, of course, significantly reduces the implementation complexity. Importantly and interestingly, some gates manipulate the transient window length. They do that, for example, by retrieving the 0 in the division by 0 from a separate input variable, and they make sure that this input variable is not cached. Loading it will take a long time and will therefore exceed the transient window. And so in order to emulate those gates correctly, we equipped WeMu with a transient window length, which is actually cache dependent. All right, let's look at one more last example of a gate, and that's the OR gate. We can see that the big difference with the AND gate is that our chain of dependencies is now split into 2 independent flows. And due to out-of-order execution on modern CPUs, those flows can execute independently and parallel to each other. So for the first case where both inputs are cached, the result is the same, the output will also be cached. But for the case where one input is not cached, we can still load the other input and cache the output variable in parallel. And again, that's the OR gate behavior that we need. As long as one input is cached, the output will also be cached. Now, you already know how it works. To emulate this in WeMu, we are of course not going to replicate a full out-of-order pipeline from real hardware, because that's extremely complex. Instead, we are going to look for the microarchitectural effect again. And the effect is as follows. Slow loads cannot complete within the transient window, so therefore instructions depending on slow loads also cannot. And in order to emulate this, we developed an algorithm called cache-aware transient scheduling. In very simple terms, it works as follows. It skips transient slow loads, it tracks the dependencies of the registers, and also skips instructions depending on slow loads, and normal instructions are executed as always. This abstraction is interesting because it allows us to model the transient out-of-order effects by traversing the instructions sequentially. So it drops the need for fancy out-of-order or parallelized execution in our emulator. And I know that the algorithm is a little bit difficult to understand like this. For full details, I'll have to refer to the paper. So enough about the implementation. Let's look at the evaluation of WeMu. To evaluate WeMu, we took microarchitectural weird machines from existing work, and we first validated them by running them on our own real hardware. And when we knew that they were correct, we then emulated them in WeMu and compared the results. And this table shows a set of microarchitectural weird machines which we tested, and it shows that WeMu is capable to correctly emulate a range of weird machines going from simple gates to very complex cryptographic algorithms like a round of AES and a SHA-1 round. For the most complex algorithms, there is an undetermined single bit error which propagates and makes the output wrong, and we still have to figure out what's happening there. But importantly, the single bit error only occurs after more than 35,000 gates have already been correctly emulated consecutively. So I still think this slide shows the potential and also the scalability of WeMu. And interestingly, WeMu is also very performant. We compared it to Gem5 for a single AND gate, and we have shown that WeMu is around 200 times faster, and Gem5 is not even functionally correct for an AND gate. We also demonstrated that WeMu is suitable for practical workflows. Specifically for the 2-block SHA-1 algorithm, you would have to wait 11.5 minutes for WeMu to complete, and for Gem5 that would take you more than a day. So to conclude now, we introduced WeMu, which is the first analysis tool for microarchitectural weird machines, making previously hidden computations observable. We introduced new microarchitectural abstractions, of which especially cache-aware transient scheduling would be interesting to transfer to other work. And we validated that WeMu is correct in most of the cases of our benchmark, and it also has speeds that could fit a practical workflow. Now, if you would be interested to collaborate, we are actively looking for people, so feel free to check out the GitHub repository or send me an email directly. Thank you.
questions for the... So I can ask the first question. How is it possible to extend the WeMu to support a new side channel? For example, accept cache side channels.
So in the code base, we made sure that you have Unicorn, and all the abstract models that I discussed here are really kind of modules. So it would be very easy to build your own module and implement and basically plug it in to the existing architecture. And also Unicorn makes it very easy, because Unicorn allows you to implement hooks that trigger on certain events. So you can, and that's also how our cache model works. So it just looks for, or it listens to memory hooks, and then it triggers your cache model. So it's very extensible. You could easily plug in the other components, but you would have to do the implementation yourself, of course.
Yeah. Yeah. So I understand speculation can be weird, but Unicorn should be deterministic, right? Especially since you're implementing it yourself, the microarchitectural model. So I'm wondering, why are you getting those errors? Do you know why? Because I mean, again, it's supposed to be deterministic, right? So presumably, if you run it again, you will get the exact same error. But why are you getting errors at all? From what I understand, it should just be slower, or it shouldn't work at all. Could you elaborate on that?
Yeah, I wish I could answer your question directly. If I could, then those errors would, of course, not be there. It's very strange, because the errors occur in iterative algorithms, like AES, where you execute the same round multiple times.
Yes.
And for the SHA-1 algorithm, the error always occurs at the same place in the 67th round of 180, I think it is, or 160, I'm not sure.
Do you think maybe just your thresholds are wrong by any chance? Or
So we played a lot with that.
Yeah.
What we suspected was maybe that some microarchitectural state from a previous round made it into the second round, but even resetting the microarchitectural state across rounds didn't work. So a very small part of me believes that it could be a bug in the actual microarchitectural weird machine, which you don't get on real hardware due to the undeterministic nature and the weird machines continuously re-executing if errors are detected. But that's a bit of a bold claim to make.
You're compiling these programs with like some previous work, I'm assuming, or how are you getting the programs to run on your weird machine?
That's the actual binaries that we import, and Unicorn does the main emulation, so it reads those binaries. We, of course, define ourselves where we need to start the execution, and we set up the memory to match what it would be in a real program execution.
Sure. Thank you.
Okay, thanks.
Good. Hi, thanks for the talk. Can you turn to slide 17, please? So I'm curious about what does it mean to skip an instruction? So you're saying you're not modeling an out-of-order execution pipeline, and yet you're skipping instructions. What do you do with them after you skip them? Or are you just making this architecturally invalid and just focusing on the microarchitecture?
Yeah, so importantly, we only skip instructions during transient execution. And after that, we roll back the architectural state, just like it would happen on a real processor. Now, the instructions that we skip, they are also skipped on real hardware because they take too long to finish before the transient window. So that's kind of our way of modeling what would happen on real hardware. But we found that real out-of-order execution is just not necessary to achieve a correct emulation. You can just skip them. On real hardware, they would never be re-executed because there happens a rollback, and we do the same.
Okay, thank you.
Yeah.
More questions? I have one more question. Is it also possible to use WeMu to reconstruct the functionality of a weird machine that you're running?
Yeah, so WeMu is really an emulator, and the output of WeMu are execution traces. And those execution traces, they show all the cache hits and misses and data races that would normally be invisible. So essentially, you could reconstruct the whole computation by looking at those outputs. But it's just not automated at this point, and that's a future research direction that we also mentioned in the paper. I don't know if that really answers.
Yes.
Yeah.
Thank you very much. Let's
Thank
thank
you.
the speaker again.
Thanks.